Welcome. Over the next stretch, we are going to build one complete skill. You will learn to take a word problem, draw it as a Moore or a Mealy machine, turn it into a state table, and finally turn that table into a real circuit. That is the exact pipeline your exams test. So let us build it one careful step at a time. Let us start from something you already know. In a combinational circuit, the output depends only on the inputs right now. Same inputs in, same output out, every single time. But now imagine a circuit that should fire only when it has just seen the pattern 101, arriving one bit at a time. Here's the interesting part. A single incoming one sometimes means almost there, and sometimes means open the gate. The output depends on what came before. That history is the missing ingredient. We call it state. A circuit that remembers its state is called a sequential circuit, and the model we use to design one is the finite state machine. Keep that word in mind, state. Here's a simple way to anchor the whole idea. Memory equals state. So let us hold two questions side by side. Combinational logic answers only one of them. What are the inputs right now? A state machine answers a second question as well. What has happened so far? Now that we know why state exists, let us define it precisely. A state is a complete summary of the relevant past. It is everything the machine needs to remember in order to decide what to do next. Keep that definition close, because everything else rests on it. Formally, a finite state machine has a few parts. There is a finite set of states. There is one state marked as the starting or reset state. There is a set of input symbols, and there is a set of transitions. A transition is simply a rule. Given the current state and the current input, it tells you which state to move to next. Let us pause and collect that. A state machine is really just four ideas. A set of states, a starting state, the possible inputs, and the rules for moving between them. Hold those four together. We picture all of this as a state diagram. Think of it as a map. Every state is a circle. Every transition is an arrow, and each arrow is labeled with the input that triggers it. Let us make it concrete with a turnstile. It has two states, locked and unlocked. From locked, a coin moves you to unlocked, while a push does nothing. From unlocked, a push sends you back to locked, while a coin does nothing. We mark locked as the starting state, the state the machine powers up in. To run the machine in your head, begin at the start state and follow the arrow that matches each input, one symbol at a time. Here's a phrase to lock in how every rule reads. Present, then next. Where am I now plus an input gives me where I go next. Now, two mistakes to watch for, and this is where many students slip. The first mistake, people invent extra states. A state should exist only if it represents genuinely different behavior. And if two states behave identically for every input, we call those equivalent states, and you should merge them. The second mistake is the classic exam killer, leaving transitions undefined. Every state needs an arrow for every possible input. Otherwise, the machine is incompletely specified. So if a transition is ever missing in an exam problem, your brain should instantly flag it as either a bug or an unstated do not care condition. Let us close this part with the key idea. A state is summarized history. A transition is state plus input gives next state. Merge states that behave the same and define a transition for every input. Remember those, and the foundation is solid. Now that we can describe a state machine, we hit the central question of this whole topic. How does it produce output? And this is exactly where finite state machines split into two families. Confusing these two families is the single biggest reason students lose marks. So let us slow right down. A Moore machine produces an output that depends only on the current state. A Mealy machine produces an output that depends on the current state and the current input. Think of it this way. In a Moore machine, the output is a property of the room you are standing in. Walk into a state, and its output is fixed. In a Mealy machine, the output is what you get for doing something while you are in that state. It depends on the input you apply on the way out. This distinction matters more than almost anything else here. So here is the retrieval phrase. Mealy minds the input. The Moore output ignores it. Let us see it on our turnstile. We will give it a real output, a one-cycle unlock pulse that physically releases the gate when you pay. As a Mealy machine, that pulse belongs to the coin transition. From lock, the moment you insert a coin, the machine outputs a 1, the pulse, and moves to unlocked. So the output rides on the transition arrow. And there are only two states. As a Moore machine, the output has to be a property of a state. It cannot ride on a transition. So we insert an extra state in between, call it releasing, and the output of that state is a 1. Now there are 3 states, and the pulse appears 1 clock later because we only emit it after the clock edge carries us into releasing. So think about what we just did. Same behavior, 2 designs, and 3 differences fall out at once. The output moved from the transition arrow into the state circle. The Moore version needed an extra state, and the Moore output arrived 1 cycle later. That is a lot, so let us anchor it firmly. The Moore output lives in the circle. The Mealy output lives on the arrow. Moore equals more states. And Mealy is fast but jittery, while Moore is steady but slow. Say those to yourself once more before we move on. Now, why is there a timing difference? Here's the mechanism, and it is worth understanding rather than memorizing. A Mealy output is computed directly from the live input, so it changes the instant the input changes. A Moore output can change only after a clock edge. Each synchronizing tick moves the machine into the state that carries that output. That is the whole reason Mealy reacts sooner. Now, a warning about a very common misconception. People think these two differ in power or that one is simply better. They do not, and it is not. Any Mealy machine can be converted into an equivalent Moore machine, back again. They differ only in when the output appears and how many states it costs. Keep that straight. Let us turn this into exam reflexes. When you see outputs written on the arrows, your brain should instantly say Mealy. When you see outputs inside the circles, your brain should instantly say Moore. And when a question asks about output timing, immediately think Mealy reacts 1 clock earlier. So the key idea for this section, the Moore output is a function of the state alone. The Mealy output is a function of the state and the input. The Moore output lives in the circle, the Mealy output on the arrow. Moore equals more states, and Mealy reacts a cycle sooner. Those few facts carry you through most of the exam questions on this topic. We can now draw a machine and reason about its output. But a drawing alone will not let us calculate or build. For that, we rewrite the machine as a state table. It holds exactly the same information, just in a form we can turn into equations. So what is in a state table? For every present state and every input, it lists 2 things: the next state and the output. You lay it out with the present state on the left. Then, for each possible input value, you record the next state, and you include the output as well. And here's the thing. The Moore versus Mealy difference appears here too, very precisely. In a Moore table, the output depends on the present state alone, so it sits in a single place tied to the state. In a Mealy table, the output depends on the state and the input together, so it is written right beside each transition. Keep that contrast in mind. It gets tested. Now, let us name the formal parts, because exams ask for the definition directly. A finite state machine is defined by a handful of things: a finite set of states, a starting state, an input alphabet, an output alphabet, a next state function, which we call delta. Delta takes the state and the input and returns the next state, and an output function, which we call lambda. For a Moore machine, lambda depends on the state only. For a Mealy machine, lambda depends on the state and the input. There is one subtle point worth keeping. A Moore machine already produces an output in its starting state before any input arrives at all. That is another reason the Moore output sequence is shifted relative to the Mealy one. 2 functions, easy to mix up, so here is the retrieval phrase. Delta moves you, lambda speaks. Delta decides the next state. Lambda produces the output. Students who blur those 2 lose marks, so keep them apart. And speaking of marks, 3 mistakes live right here. First, under time pressure, people swap the present and next entries. So anchor yourself. The present state is the input to the rule. The next state is the result. Second, in a Mealy table, students attach the output to the next state, but the output belongs to the transition, not the destination. Third, when a question asks for both the next state and the output, people give the next state and forget the output entirely. So here are the exam reflexes. If a problem hands you a diagram and asks for the table, immediately think 1 row per state, per input, then fill in the next state and the output. And if it gives you the table and asks for the diagram, you simply run the same logic in reverse. In one line, here is the whole idea. A state table is just delta and lambda written out as a grid. Present state in, next state and output out. The output sits with the state for Moore and with the transition for Mealy. Up to now, everything has lived on paper. Now comes the satisfying part. We turn that table into real hardware. The circuit has two parts. There are flip-flops, which store the current state, and there is combinational logic, which computes the next state and the outputs. Here is the timing idea that ties it all together. The flip-flops update only on the clock edge. In between edges, the logic computes the next state and the outputs from the present state and the inputs. That feedback loop, present state in, next state stored on the next tick, that loop is the machine actually running. Keep that picture. It is the heartbeat of every state machine. Step 1 is state assignment. You give each state a binary code. This code is just a label, a design choice, but it changes how much logic you will need. Now, how many flip-flops do you need? The reasoning is simple. Each flip-flop stores one bit, and a small number of bits can label a large number of states. Concretely, the number of flip-flops is the log base 2 of the number of states, rounded up. That rounding is where people slip, so let us anchor it. The number of flip-flops equals the log base 2 of the number of states, rounded up. So 5 states need 3 flip-flops, not 2. Keep that. There is also a second style called one-hot encoding. Here you use one flip-flop per state, with exactly one of them high at any time. It costs more flip-flops, but it gives you simpler, faster next state logic. Step 2. Pick a flip-flop type and find its inputs. For a D flip-flop, the next state bit is just the D input. There is nothing to compute. Remember it this way. D is the easy one. D simply equals the next state. But for a JK flip-flop or a T flip-flop, you need the excitation table. The excitation table tells you which inputs drive each required change. From 0 to 0, from 0 to 1, from 1 to 0, and from 1 to 1. Now pause, because here's the single most common synthesis mistake. People reach for the characteristic table, which tells you the output given the inputs, when what they actually need is the excitation table, which tells you the inputs needed to reach a desired output. Those are opposites. The JK excitation table also has free entries, values you may set to 0 or 1, called do not care entries, and you must take advantage of them in the next step. Let us catch our breath with a quick summary. So far in this build, 3 moves. You encoded the states. You counted the flip-flops with log base 2 rounded up, and you built the excitation table for your chosen flip-flop. Hold those 3. Step 3, minimize. You take each flip-flop input and each output and simplify it using a Karnaugh map, using those do not care entries. From the map, you read off the simplified equations. Step 4, you draw the gates and wire them back to the flip-flops. Let us make this concrete with the Mealy turn style. We encode locked as 0 and unlocked as 1. There are 2 states, so we need just one flip-flop, because the log base 2 of 2 is 1. With a D flip-flop, its input is read straight off the next state column, and the unlock pulse output is a Mealy function of the state and the input. In plain words, the pulse is a 1 exactly when the state is locked and the input is a coin. That is the idea that the output depends on the state and the input, now turned into a real gate. So, exam reflexes once more. When a problem says, implement this with D flip-flops, immediately think, the next state bits go straight to the D inputs, then minimize the outputs with a Karnaugh map. When it says JK, immediately think, build the excitation table first, then use a Karnaugh map with the do not care entries. Here's the whole section in one breath. Synthesis is a fixed pipeline. Encode the states. Count the flip-flops with log base 2, rounded up. Build the excitation table for your flip-flop. Minimize with a Karnaugh map using do not care entries. Then draw the circuit. Same 5 steps every time. We now have every piece. So let us put them all together on the problem you will actually meet on an exam, the sequence detector. It outputs a 1 whenever it has just seen the pattern 1, 0, 1 in a stream of bits arriving one at a time. The first thing to decide is whether it is overlapping or non-overlapping. Overlapping means the trailing 1 of one match can start the next match, so the stream 1, 0, 1, 0, 1 produces 2 detections. Non-overlapping means you reset after each match, and you get just 1. That single choice changes the diagram, and forgetting to ask it is a classic trap. Keep it in mind from the very first line. Let us build it as a Mealy machine first. The states are simply the meaningful prefixes of the pattern. One state means you have seen nothing useful yet. A second means you have seen a 1. A third means you have seen a 1 and then a 0. From that third state, an input of 1 completes the pattern. On that transition, the input is a 1 and the output is a 1, so the output fires right on the transition. And in the overlapping version, that same incoming one also sends you back to the second state, the one for having seen a single one ready to reuse that trailing bit. Now let us build the Moore version of the same detector. Because the output must live inside a state, you add a dedicated detected state whose output is a 1. And here is the consequence. The Moore machine needs one more state than the Mealy one, and its output appears 1 clock later. There it is again, in the wild. More equals more states. Now the common mistake, and it is a costly one, in the overlapping case, people send the machine back to the start state after a detection. But that throws away the trailing one, and you miss the overlapping matches. So always ask where the useful suffix of the pattern leaves you. So when an exam asks you to design a sequence detector, immediately think the meaningful prefixes of the pattern are my states. Then decide overlap. Then choose Mealy for fewer states or Moore for a clean clocked output. Let us reinforce this one because it appears constantly. The states of a detector are the prefixes of the pattern you are hunting for. Overlap decides where you return after a match. Mealy fires on the transition. Moore needs an extra state and fires a cycle later. We can now build both versions of a machine. So now comes the real engineering decision. Which one do you choose? This is exactly where the conceptual exam questions live. Mealy uses fewer states and it reacts to cycles sooner, but its output is computed directly from the live input. So if the input glitches, the output can glitch too. And here is a subtle point. That is not a bug you fix. It is simply inherent to Mealy. If you need a clean output, you have two choices. You can use a Moore machine whose output changes only on a clock edge. Or you can register the Mealy output, which means passing it through a flip-flop. But that gives back the one cycle speed advantage. So here is a guaranteed exam question. What happens when the input changes between two clock edges? With a Moore output, nothing changes until the next tick. With a Mealy output, it can change immediately. Rehearse that contrast. You will use it. Now, conversion, which is another favorite exam task. To turn a Mealy machine into a Moore machine, you split each state so that every distinct combination of state and output becomes its own state. And that, by the way, is exactly why Moore ends up with more states. To go the other way, from Moore to Mealy, you move the output of each state onto the arrows coming into it. So if an exam asks you to convert from Mealy to Moore, immediately think one more state for each output a state can produce. A quick word on encoding choices. Binary encoding minimizes the number of flip-flops. One-hot encoding minimizes and speeds up the logic, but it costs more flip-flops. Neither one is wasteful. They are simply 2 points on a trade-off. And on reconfigurable chips, one-hot is often the better choice. So remember this pair of phrases. Mealy is fast but jittery, while Moore is steady but slow. And binary means fewer flip-flops, while one-hot means simpler logic. The takeaway for this section: choose Mealy for speed and fewer states. Choose Moore for a clean clocked output. Mealy glitches are inherent, not bugs. You convert from Mealy to Moore by splitting per output. And encoding is a trade between flip-flop count and logic complexity. We have covered a great deal, so let us pull the entire topic together. The whole subject is really one pipeline. Word problem into state diagram into state table into encoded equations into a circuit. If you can walk that path, you understand finite state machines. Now let me give you the phrases to carry into the exam. Listen for them. Memory equals state. Present, then next. The output is in the circle for Moore and on the arrow for Mealy. Mealy minds the input. Delta moves you. Lambda speaks. Moore equals more states. Mealy is fast but jittery, while Moore is steady but slow. The number of flip-flops equals the log base 2 of the number of states, rounded up. And D is the easy one. Master those phrases and the worked pipeline, and you can solve essentially any finite state machine question on an exam. And here is the bigger reward. You have just described in miniature exactly how the control unit of every processor works. The natural next step from here is implementing these machines in a hardware description language, such as Verilog or VHDL. So, to leave you with the shape of it all: 1 pipeline, 2 output models, 9 short phrases. That, in full, is the topic.